5,000-pound satellite is plummeting toward Earth, and its fiery descent could leave debris scattered across the planet. The European Space Agency's ERS-2 satellite is making an uncontrolled re-entry, with chunks of its 2.3-ton mass likely to survive the intense plunge through the atmosphere. As scientists predict its fall with a margin of uncertainty, the world watches and wonders, where will the remnants of this celestial titan land, and what implications will it have for our understanding of space debris management? Background on ERS-2 and its mission. ERS-2 was launched on April 21, 1995, as part of ESA's mission to monitor environmental changes and gather data on the Earth's surface and atmosphere. It carried an array of sophisticated instruments, including the Advanced Synthetic Aperture Radar, ASAR, a radar altimeter, and various sensors for measuring sea surface temperature, ocean surface winds, and atmospheric conditions. Over its operational life, ERS-2 provided invaluable data that contributed to numerous scientific studies and practical applications such as climate monitoring, disaster response, and maritime surveillance. Predicting the re-entry. The exact time and location of ERS-2's re-entry are subject to significant uncertainty due to the complex interplay of factors influencing its descent. As of the latest prediction issued by ESA's Space Debris Office, the satellite is expected to re-enter the Earth's atmosphere at approximately 12:05 p.m. EST, 1541 GMT, on Wednesday, February 21st, with a margin of error of plus 1.44 hours. This uncertainty primarily stems from the variable effects of solar activity, which alters the density of the Earth's atmosphere and consequently affects the drag experienced by the satellite. Atmospheric re-entry dynamics. Re-entry dynamics involve the interaction between the spacecraft and the atmospheric layers it traverses. As ERS-2 descends, it encounters increasing atmospheric density, leading to rapid deceleration and intense heating due to frictional forces. This process, known as ablation, causes the spacecraft's exterior to heat up and shed material. For most satellites, this results in the complete disintegration of the structure before reaching the Earth's surface. However, certain components, especially those with high melting points and structural integrity, can survive the descent. Survivability of ERS-2 components. Simona Elena Nichiteanu from ESA's European Space Operations Center, ESOC, indicated that between 10% and 20% of the satellite's mass might survive re-entry. The heaviest and most robust components, such as fuel tanks, internal support panels, and the synthetic aperture radar, SAR antenna, are most likely to endure the fiery descent. The survival of these components raises important questions about the potential hazards posed by falling debris and the need for effective tracking and mitigation strategies. Impact, prediction, and potential hazards. The primary challenge in managing re-entering space debris lies in accurately predicting the impact zone. Given that the Earth is predominantly covered by oceans, there is a high probability that surviving fragments of ERS-2 will splash down into the sea. However, the possibility of debris reaching populated areas cannot be entirely ruled out. This necessitates continuous monitoring and coordination with global space agencies to issue timely warnings and take precautionary measures. Orbital debris, management and regulation. The uncontrolled descent of ERS-2 serves as a stark reminder of the ongoing issue of space debris. With thousands of defunct satellites and spent rocket stages orbiting the Earth, the risk of collision and subsequent fragmentation increases, leading to the generation of more debris. This Kessler syndrome, a scenario where the density of objects in low Earth orbit, LEO, is high enough to cause a cascade of collisions, poses a significant threat to both active satellites and manned space missions. Michael Runnels, an assistant professor of business law at California State University, Los Angeles, emphasizes the need for enforceable orbital debris regulations. The absence of stringent regulatory frameworks means that many satellites are launched without adequate deorbit plans, increasing the likelihood of uncontrolled re-entries. Effective regulation would require satellite operators to design spacecraft with end-of-life disposal mechanisms, such as controlled re-entry or transfer to a graveyard orbit. Technological solutions for debris mitigation. Several technological solutions have been proposed and are under development to address the space debris problem. These include active debris removal, ADR techniques, such as robotic arms, nets, harpoons, and laser ablation. Each method presents its own set of technical and economic challenges, but the overarching goal is to reduce the number of debris objects in orbit and prevent future accumulation. For instance, ESA's ED-orbit mission aims to demonstrate the feasibility of capturing and deorbiting a defunct satellite using a robotic arm. Similarly, Japan's Aerospace Exploration Agency, JAXA, is exploring the use of electrodynamic tethers to reduce the orbital lifetime of debris. These innovative approaches, coupled with international cooperation and regulatory oversight, are crucial for ensuring the long-term sustainability of space activities. Case study: ERS-2's operational legacy. ERS-2's contribution to environmental monitoring and Earth observation has been significant. During its operational period, the satellite provided continuous data that enhanced our understanding of climate change, oceanography, and atmospheric science. The SAR instrument, in particular, enabled high-resolution imaging of the Earth's surface, facilitating studies on deforestation, urbanization, and natural disasters. The data collected by ERS-2 has been used in various applications, such as monitoring ice cover in polar regions, assessing the impact of oil spills, and tracking the movement of tectonic plates. This legacy underscores the importance of satellite missions in advancing scientific knowledge and informing policy decisions related to environmental protection and disaster management. Future implications and research directions. The re-entry of ERS-2 highlights several areas for future research and development in space debris management. These include improving predictive models for re-entry trajectories, enhancing tracking capabilities for small debris objects, and developing more robust materials and designs for spacecraft to minimize the risk of fragmentation. Furthermore, there is a need for comprehensive studies on the long-term effects of space debris on the orbital environment and the potential risks to both space-based and terrestrial infrastructure. Collaborative efforts among spacefaring nations, coupled with advancements in technology and regulation, will be essential in addressing these challenges and ensuring the safe and sustainable use of outer space. Conclusion. The uncontrolled re-entry of ESA's ERS-2 satellite serves as a poignant reminder of the complexities and risks associated with space exploration. As the 2.3-ton spacecraft descends towards Earth, it brings into sharp focus the need for effective space debris management and regulatory oversight. While technological advancements offer promising solutions, international cooperation and robust regulatory frameworks are critical for mitigating the risks posed by space debris and ensuring the sustainable exploration of outer space. The scientific community must continue to monitor and study re-entry events like that of ERS-2 to improve our understanding of orbital dynamics and the behavior of space debris. This knowledge will be instrumental in developing strategies to protect both space assets and human life on Earth from the potential hazards of re-entering spacecraft. As we venture further into the cosmos, the lessons learned from ERS-2 will guide us in safeguarding our planet and ensuring the responsible use of space for future generations. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.